today discuss the some basic properties of the some basic properties of the elementary particles and fundamental forces in nature. We know that the nucleus of an atom is made of protons which are positively charged and neutrons which are electrically neutral. Protons and neutrons are made of more fundamental particles called quarks. This we know from scattering experiments, which tells us information about the interiors of protons. So, there are different types of quarks. Two such different quarks are called up type quark and down type quark, and protons are made of two up type quarks and one down type quark. Neutrons are made of two down type quarks and an up type quark. They are fractionally charged. The up type quark is made of minus up type quark is plus 2 by 3 times magnitude of the electronic charge E. The charge on the down type quark is minus 1 by 3, it is negatively charged, and the magnitude is minus 1 by 3, 1/3 of the charge of the electron magnitude. So, between two U quarks and D quarks, total they have 1 unit positive charge in units of electronic charge. Electrons on the other hand are found to be structureless. Okay, we do not, so far as the experiment goes, they have no structures. All matter around us are made of these fundamental particles, U quark, D quark and electrons. And another particle which was known, this was proposed by Wolfgang Pauli in connection with the beta decay. In the beta decay experiments, the electrons coming out of the nuclei were found to have a continuous energy spectrum, which is not expected if final state had only an electron in addition to the daughter nucleus. If it was only a daughter nucleus and an observed electron beta particle in the final state, then we could have calculated the energy, kinetic energy of the emitted beta particle from the mass relations between the masses of the daughter nucleus and the parent nucleus, and using the kinematic relations, energy momentum relations. But that was not the case. So, the way out was proposed to have another particle in the final state, which is not observed at all, and this was supposed to be a massless particle, chargeless particle, weakly coming out in the or interacting with electrons and the atomic particles, nuclear particles. And that was the story at that time in 1930s, and later on in the period of 30s to 50s, many new particles which was otherwise not present in ordinary matter were found in what is now known as cosmic rays. The cosmic rays are basically radiation coming from outer space, outside the earth. It could be partly from sun, it could be from other stars, or it could be from other sources, astrophysical sources. These radiations, it has electromagnetic radiation as well as particle content in it. There are charged particles and neutral particles. Some of these particles are exotic compared to the naturally available particles, elements on earth. So, there are many of them which was discovered. One is called muon, which was later found to be very similar to the electron, but much heavier, 200 times heavier than the electrons. There were other particles called pions, kaons, lambda particles, etc. Muons were like electrons, elementary in the sense that they are not made of some finer particles or more fundamental particles. Whereas, the other set pion, kaon, lambda, etc. are later on found to be made of quarks like neutron and protons. So, these particles were also discovered in various laboratory experiments. So, scattering experiments were going on, and then we could also produce all these particles in scattering experiments. And these experiments, collider experiments, also discovered many other particles which were not even present in cosmic rays. So, thus there are lot many subatomic particles that were discovered in the 20th century. We will not go into the historical details or even attempt to actually give a overview of that. Rather, we will refer to some of these books. We could take any other book, but I just mentioned two of them. One is Particle Hunters, which is a very readable book for students, telling the discoveries and other aspects of particles, giving a very good introduction to this many times without going into the details and emphasizing sometimes on the historical aspects, etc. So, if you are interested in it, you can go through this Particle Hunters by Niemann and Kirsch. Another book is Conceptual Foundations of Modern Particle Physics by Marshak. It is also a very good book which gives a good introduction to all these developments at the early stages and the discoveries. We will actually here sum up the knowledge that we have now. The very elementary particles are categorized into two different distinct classes. One is called leptons, to which belongs electrons, muons and tau leptons. All of these have something in common. We will come to some of the details as we progress. All of them have one unit of negative charge, again in units of electronic charge. So, obviously, electron will have -1 charge, and muon and tau also are found to have the same charge, electric charge. But the masses are different. Electron is the lightest one with mass 0.5 MeV per c square. Muon is 200 times heavier than this, 106 MeV per c square, and tau lepton is much heavier. It is 1777 MeV per c square, or 1.7 or 1.8 GeV per c square. These are three particles under leptons, three charged particles under leptons. Then there are three other neutral particles which are called neutrinos. There are three of them, each one linked with either electron, muon or tau. All of them are neutral, electrically neutral. All of them are very light. In fact, in the standard model of particle physics, they are assumed to be massless, and mass is equal to 0 strictly. But recently, last 10 years, we know that 10 or 15 years actually, we know that these particles are not really completely massless. They have some mass. We do not know yet what their masses are. We have some information about the difference of their masses, but they are very light. Light in the sense that they are something like of the order of a few electron volts masses. So, I have put a question mark there just to remind you that when I say mass equal to 0, that is with all these caveats. This electron type neutrino, E neutrino, is the one which is produced in the beta D. Strictly speaking, it is not exactly the neutrino, this particle, but it is the antiparticle of this which is produced in the beta decay. We will come to what an antiparticle is at some stage. So, but it is of that type, I mean, and muon type neutrino or antineutrino are not produced in beta decay. They are produced only in association with mu lepton. Similarly, tau leptons. That is one thing. And the other part of the spectrum is called quarks. The up type and down type quarks we already saw inside the proton and inside the neutron. And as I mentioned at that time, the electric charge of up type quark is plus 2 by E in units of electronic charge. Mass of that is roughly 2.3 MeV per c square. Down type quark has an electric charge of minus 1 by 3, mass slightly heavier than U quark, 4.8 MeV per c square. Charm quark is similar to the U quark, electronic charge is 2 by 3, mass is 1275 MeV per c square. There is another type quark which are called strange quarks. Electronic charge is minus 1 by 3, heavier 95 MeV per c square, heavier compared to the D quark and U quark. Then comes top quark, which is again similar to U and C. Charge, electronic charge is plus 2 by 3, mass is 173.5 GeV per c square. It is an elementary particle which is something like 200 times, 174 times heavier or 180 or more times heavier compared to the proton, heavier than the proton, and it is an elementary particle. It is an elementary particle in the sense that it is not made of any further finer structure, and in the dynamics of elementary particles, this top quark is one of the crucial components. It plays a crucial role in many cases. In another quark is B quark or bottom quark, charge is minus 1 by 3, mass is 4.18 GeV per c square. So, you see that I have put a question mark on all these masses except for the top quark. That is because except for the top quark, all the other quarks are really not found in free state. Therefore, when we say the mass of this particle, we have to qualify that statement with various other things. It is the mass of the particle as inferred indirectly, and there again the precise definition of mass itself is somewhat hazy. Okay. So, we have to keep in mind that when I say the mass of this particle, it is some notion of mass of the particle, and then that is not a very precise definition, precise quantity like the mass of the particle, like the mass of the top quark or proton, etc., that we can measure. Whereas, in the case of top quark, these particles are so heavy that they are not really found in bound states. They are actually you produce them and they decay immediately, very unstable particle. Many of these particles are unstable. Top quark is also unstable, muon is unstable. You do not really see them freely moving around for ages. They are produced in some reactions and then they decay in some short while, and top quark is also like that. U quark, they can be made into protons and which can stay for a long time, and then in fact they do not decay for a they do not decay, they are very, very stable. And similarly, you can have bound states of charm quarks, bound states of strange quarks, combinations of these, bound states of B quark, etc. Many of these bound states are unstable, but they all form bound states. They do not really decay as a B quark. This is slightly different from saying that top quark decays. A B quark immediately combines with some other quark, another B quark or some other quark, to form bound states. But top quark actually, when it is produced, it decays immediately. The decay time is so short that it cannot even combine with some other quark within that short time. So, they have such short decay time, and therefore, from the decay products actually we can infer the mass of this particle very accurately. Mass of a particle is basically can be a working definition can be that the energy of the particle, the total energy of the particle in its rest frame. So, when the particle is at rest, it is not moving, it has no momentum, it has no kinetic energy. So, the only energy that it has is due to its mass. So, that is the mass of the particle, say one definition. Now, so that is basically the picture of the elementary particles that we know of now, and the other part of this discussion is basically the fundamental interactions. Gravitational interaction is all around us, and then we know a lot about them, about this planetary motion, apples falling or anything. Anything that has mass or energy can take part in or does take part in gravitational interaction. Then we have electromagnetic interaction, which is also very well known. We have it all around us. Light that I see you and you see me is an example of electromagnetic interaction, or I flex my muscle, or I pick up something, and all these forces, or muscular force or anything that has to do with our body mostly is due to electromagnetic interactions or electromagnetic force. Okay. Atomic spectra. So, that is another thing that you know, and any particle having electric charge has electromagnetic interaction or takes part in electromagnetic interaction. Weak nuclear interaction, we know that there are electrons coming out of nucleus. The electrons do not exist there prior to this, but they are produced in what is called beta decay of the nucleus, and they are ejected from the nucleus. So, that is one instance of beta weak interaction, but there are other weak interactions that we have well understood, and but that is not naturally occurring. We have to actually go to laboratory experiments like collider experiments, LHC experiment or LEP experiment that we mentioned earlier, or any other experiment that is going around, and for weak interactions. And we can associate the weak interaction to a charge, quote unquote charge, which is called the weak isospin of the particle, a property of the particle which is called weak isospin. So, if the weak isospin of the particle is 0, then they will not take part in weak interaction. Then there is strong nuclear interaction. Obviously, we know about that. They are there because nucleus is held together, many protons are held together in a nucleus despite their positive charge and repulsion, electromagnetic repulsion. So, there has to be some strong nuclear force, and the cause of this can be associated with some other property which is called color charge, strong color charge of the particle. Now, we cannot at some stage at high energies separate this electromagnetic interaction and weak interaction. Instead, we are forced to talk about them as a combined force, which is called electro-weak interaction. This combining, mixing of this joining of these two is similar to the electromagnetic interaction, which is a combination, well, in some sense, of electric and magnetic properties of the matter. I should say the other way around. Actually, electromagnetic interaction cannot be separated into electric and magnetic forces or interactions. Many cases, including when the charged particle are moving, are in motion. Okay? So, you cannot separate this electromagnetic interaction into electric and magnetic forces unless you go to very small non-relativistic cases. So, now in a similar fashion we can actually combine, we have to think about a combined electromagnetic force rather than an electric combined electro-weak interaction rather than an electromagnetic and weak nuclear interaction separately. Coming to the strengths of these interactions, gravitational, so let us take a particular case of a proton-proton separated at say 10 power minus 10 meters or 1 angstrom. What is the gravitational interaction between these? Gravitational force say is g mp square over r square, which g is the gravitational constant 6.674 into 10 power minus 11, and then mass of the proton is 1.673 into 10 power minus 27 kilogram. Square of that has to be multiplied with the g, divide that by the distance 10 power minus 10 square meters. This gives us something like 1.868 into 10 power minus 44 Newton. Take the same proton and combine it and find out what is the electromagnetic interaction between these two when they are separated by 1 angstrom. It is equal to E square over E is the charge, E square over 4 pi epsilon 0 r square. Numerically it is E is 1.6 into 10 power minus 19 coulomb, square of that divided by 4 into pi 3.14 into 8.85 into 10 power minus 12, which is epsilon 0 into r square. Turns out that it is equal to 2.3 into 10 power minus 8 Newton. So, if you compare the electromagnetic force, the strength of the electromagnetic force with the strength of the gravitational force, you see that it is something like 10 power 36 times stronger compared to gravitational force, which is very strong compared to the gravitational force. So, let us see how the other interactions are. If we consider the strong interaction to be of strength say 1, then electromagnetic interaction is 100 times weaker than this. Weak nuclear interaction is 10 power minus 3 times weaker than the strong interactions, or 10 power minus 11 times weaker than the electromagnetic interaction, and gravitational interaction is very weak, 10 power minus 38 times weaker than strong interaction. So, in most of the elementary particle physics studies, we actually neglect the effect of gravitational interaction, because when we consider say proton-proton collision at LHC at 70 eV or 80 eV center of mass energy, we have effect of strong interactions, weak interactions, electromagnetic interactions, etc. And if you consider the gravitational interaction along with that, if what we are saying here is the right thing, then we will not have any effect of this compared to the other 3 interactions. Okay. So, basically we actually do not really consider this here. The other reason is that we do not still have a good good model for quantum gravity. We do not know what is gravity like at very small scales. Only what we know so far is that even at 1 Fermi scale 10 power minus 15, we do not have the effect of gravity observed so far, and Newtonian gravity is tested up to micron level. So, less than millimeter level, sub-millimeter level, we know that it is gravitational interaction is like the Newtonian gravity. So, therefore, it is very weak at that stage. Beyond that, we do not really know, but if we believe we can take the extend this idea of gravitational interaction that we have at larger scales, then it is going to be very weak until we reach very high energies. All these strengths actually are again scale dependent. So, this is not strictly a constant, you see. At high energies, at energies of Planck scale, say 10 power 19 GeV, we can expect the gravitational interaction to be of the or at a comparable strength compared to other interactions. So, and the other interactions also evolve with energy scale. So, the statement is taken to be taken with some caution, but by and large this is a kind of a guiding principle when we actually look at the strengths of these interactions. Certainly at the scales that we deal with in the normal case, but atomic and nuclear scales, but it is also valid even to a slightly higher scale. Now, how do we understand these interactions? Let us look at electromagnetic interaction between two electrons. Okay, same. So, if you consider an electron interacting with an electron, we can think about it as if, say, electrons exchanging some particles, some information in terms of the quanta of electromagnetic, which is called a photon. Okay. So, we have an exchange of information from one electron to the other, or exchange of something, quantum of the electromagnetic field, or exchange of photons between these electrons, and that is how the interaction happens. That is how we understand it presently. So, diagrammatically I can represent one electron by an arrow, the other electron by another arrow, blue arrow, and exchanged photon by a wavy line, the orange wavy line. See. So, they represent this particular picture, then represent the electromagnetic interaction between two electrons. See. So, we can say in some sense that the photons are the carriers of electromagnetic interaction. This is true not only between the electrons, but between any charged particle. Electromagnetic interaction between any charged particle is thought of happening through the force carriers photons, or the exchange of the force carriers photons. In exactly similarly, we can think about weak interactions between electrons, right, and but now the interaction is different, therefore, the force field is different, and therefore, the carrier is different. So, the first carrier here is called as a Z boson. Okay. This particle is exchanged, some quantum of the weak field is exchanged between electrons, and then that is basically the interaction between the electrons. And when we talk about strong interactions, electrons do not take part in strong interactions. We will come to the details later. So, quarks, when they interact strongly, they exchange some quantum of strong field, which is called gluon. To sum up, electromagnetic interactions are due to what are called photons. We usually label it a photon by the Greek letter gamma, and the mass of the photon is 0. Photon is strictly massless. Weak nuclear interaction is due to the exchange of happens via the carriers called Z bosons and W bosons. Z boson is electrically neutral and massive with mass around 100 GeV per c square. W boson is electrically charged, one unit of either plus charge. There are two types of W's, plus and minus. So, one of them is charged like electron, the other is charged like the proton, and they also have similar mass, about 100 GeV. Well, it is actually 80.4 GeV or so for W and 91.19 GeV for Z boson, roughly 100 GeV. And the gluons are again massless, and they are electrically neutral, but they carry strong color charge. So, they can interact very strongly between themselves, and there are different types of them. There are actually 8 such different type of quarks, gluons that we have in nature to account for the strong interaction. Coming to the other particle, which is a totally different species on it in itself, completely different from the ones that we have been talking about so far, leptons and quarks. This is called the Higgs boson. The standard model particle physics requires this particle, okay, to generate masses for the matter particles as well as the gauge boson particle. We said electron has mass, proton has mass, Z boson has mass. To explain this presence of the mass of the particle, we need to have some mechanism by which masses are generated or generated for the particles, and this in turn needs what is called the Higgs field, and consequently we have a physical particle called Higgs boson, which is a scalar particle, meaning spin of this particle is 0, and that particle itself has mass. The mass itself is not dictated by the standard model, it is not known into the standard model. It has to be fixed from experiments like any other mass of the other particles. Okay, so with the discovery of the Higgs particle, then we have the table of elementary particle. Here we discussed the leptons and the quarks, okay, and that is the same as what we had seen earlier. Force carriers we discussed, and then there is electromagnetic force and electromagnetic field, and photons are the carriers of electromagnetic field, and the weak nuclear force has Z and W plus minus as the carriers, strong nuclear force has 8 gluons with this, and the Higgs field here. So, this particular chart basically combines all the known or lists all the known particles and some of their properties. Okay. So, with that I think we will stop here today, and then we will continue our discussion tomorrow in the next lecture.